Okay, so you have a test tomorrow. What do you need to bring? Pencil. What else? Calculator is super important. Probably the calculator is more important than the pencil. Okay, but you should have both. Okay, so make sure you have both. Don't worry about your formula sheet. I put the formulas on the front of the exam because I don't know how much you've written to yourself on your formula sheet. And so you can't have your formula sheet. You can just have the one that's on the front of the test. Okay, so there'll be a multiple choice form and there'll be an exam booklet. Okay, and you can write in the booklet. In fact, you have to answer the written response stuff. So that's how that will work. And then fill in your multiple choice answers on the zip grade form, and then you will be set. When can you start? You can start in lunch if you want to. Okay, so this class normally starts at 12, 11. Okay, so I'll say you can start maybe a little bit before noon. Okay, maybe even 10 to noon, let's say. Okay, that'll give you an extra, what are we looking at? Yeah, 20 minutes. Okay, and then if you need a couple of minutes into nighttime, okay, I'll let you go a couple of minutes into nighttime. Reason I can't let you go too far into nighttime is that's how I'm getting the extra 20 minutes for my period 4 class. And because a few of them have to catch the bus and they can't write after 3:30. Okay, so that's how we'll get everybody an extra 20 minutes if they want it. Okay, if of course you usually write in learning support or have other accommodations for writing exams, I have already got my list and I will have those set up and waiting for you in the appropriate locations if that applies to you. Okay. All right. So, Newton's first law. Now, Newton's first law is not something like that a lot of people know of, okay, in terms of like the wording of it. But it is something you experience all the time, okay? A few of you saw me bringing this in at the start of class. Okay, I have this like terribly full glass of like water with green food coloring in it so you can see the water. Okay, why am I walking so slow? Why am I being so careful? Because it might what? Okay, if I was like, I could like slowly speed up here, but what happens if I stop? I spill. What? I stopped. What did the water do? It kept going. Okay, that's Newton's first law. Okay, we all know it. We've experienced it lots of times. Okay, we all know how Newton's first law works, but not everybody understands kind of the wording of it. Okay, the reason that happens, one word: inertia. Okay, an object in motion remains in motion at a constant velocity until acted upon by an external unbalanced force. Okay, that is Newton's first law. Okay, an object at rest remains at rest unless acted upon by an external unbalanced force. In other words, Newton's first law says that this desk will stay right there, provided nobody touches it. Well, duh. Of course it won't go anywhere unless nobody touches it. Okay? That's just nature. Okay? We just know that intuitively. Right? But that's Newton's first law. It's not rocket science. It's part of rocket science, but in and of itself it isn't rocket science. Okay? It's common sense. Okay? It is because of Newton's first law that it is the law to wear your seatbelt. Because if you get in a car accident and you're not wearing a seatbelt, what happens to you? You're going to get hurt really badly. Because Newton's first law. The car stops and you're not attached to it by a seatbelt. You continue to move at the velocity you were moving at when the car was in motion until acted upon by an external unbalanced force. Usually something hard and unpleasant. Steering wheel, windshield, other cars, the road, okay? Things that can hurt you really badly. That's why you gotta have your seatbelt on. Okay? Your seatbelt prevents Newton's first law from hurting you. Well, I mean, that's not true. If you've ever been in an accident with your seatbelt on, Newton's first law still hurts you. You get a nice bruise, exactly the same shape as your seatbelt, okay, right across your chest, because you hit it pretty hard, okay? Now, how does your seatbelt work? You ever get in, you're in a rush, you grab the seatbelt and it just won't come out, right? And you just sit there and you keep pulling on it, but it won't come, and you know you have to stop, take a deep breath, let it back, and then pull it out slowly. Okay? Your seatbelt works on Newton's first law as well. Okay? That catch mechanism is actually activated by a pendulum. So there's a little pendulum inside the mechanism that retracts your seatbelt. And if you stop suddenly, the pendulum swings forward and it catches, it tilts a locking bar up into the ratcheted wheel that normally allows your seatbelt to unwind. It catches in that ratcheted wheel, and the seatbelt can't come undone, or it can't come out. Okay? If you're traveling along at a constant speed, you can move your seatbelt, no problem, because the pendulum is just hanging there, moving at the same speed as the car. If the car stops suddenly, it swings forward and locks in place your seatbelt. Your airbag works on the same idea. Okay? In fact, the sensor that activates your airbag is the same kind of sensor that your phone uses to tell it which way it's oriented. Right? So if you're looking at your phone this way, portrait, and then you flip it to landscape, it rotates. Because inside there is a ball, essentially inside some wires, and when that ball changes position, it activates a different circuit and the screen flips. Okay? Well, your airbag has basically a metal ball inside a cage. Okay? And if you stop suddenly, the ball will move forward and touch the wires, complete the circuit, and detonate the airbag. Okay? But it only works if the acceleration is sufficient. Okay? It won't move far enough forward if you're just in a minor crash where you slam on the brakes and you don't actually hit anything. The airbag, thankfully, doesn't detonate in those situations. Okay? They rely on Newton's first law. If the car stops suddenly, things inside the car want to keep going. Okay? And we can use that to our advantage to keep it from hurting us. It's strange, but it's true. We actually use the thing that can hurt us to keep it from hurting us. Okay? Most of the stuff in your car relies on Newton's first law. Okay? Now, when there is an unbalanced force, what will happen to the velocity, to the object? It'll accelerate. Okay? Remember that when I quoted that law, I said, an object in motion remains in motion at a constant velocity until acted upon by an external unbalanced force. An object at rest remains at rest until acted upon by an external unbalanced force. As soon as there's an unbalanced force, then velocity is going to change. The object is either going to accelerate, well, it's going to accelerate. It's either going to be positive or negative. Okay? It's either going to speed up or slow down or change direction. Okay? Everyone follow me there? Okay. Now, the greater that force, the greater the acceleration. That's Newton's second law. Okay? We'll talk about that one another day. Okay? But the two are very much related. Okay? Making sense so far? So Newton's first law, all that stuff I said about staying at a constant velocity until it's acted upon, that can be all summed up in one word, and that word is inertia. Okay? Newton's first law is inertia. Okay? And we know all about it. It is that thing that can be very convenient or very inconvenient. Like when we get our first snowfall. Okay? And it gets icy. And everyone's still driving like it's summertime. Okay? And they're coming up to the stop sign and they hit the brakes and they just keep right on going. Okay? Because the unbalanced force they were hoping for isn't there. Or it's not as big as it usually is. Okay? Not enough friction or no friction, and you just keep right on going. Okay? And the same is true on a corner. Okay? How many people have ever watched Canada's Worst Driver? I watch it sometimes, and then I have my faith in humanity destroyed, and then I don't watch it again for a while. Okay? But if you take a corner too fast and it's slippery, you continue to move at a constant velocity. Straight. Okay? If you actually make the turn, it's because you're accelerating. velocity is a vector quantity. Even if the magnitude of my velocity doesn't change, I change direction. Turning requires an acceleration. It requires a force. That force is friction. Okay? If it's not there, you keep going straight. Okay? And then that's bad usually, because usually there's stuff there that's, you don't want to hit. Okay? Making some sense? Okay, is this a big deal if you're an astronaut? It is. We take for granted on Earth that there's friction and gravity because the two kind of depend on each other. Okay? If I'm in space, okay, and I get moving, how do I stop? I would have to grab something or exert a force in the opposite direction if I want to stop. But if I'm just in my spacesuit, okay, and I don't have any little, reaction control thrusters on my suit, if I'm moving, I'm gonna keep moving. Okay? And there is nothing I will be able to do. Flailing my arms is not going to do anything except make me look panicked, which I would be. Okay? I would have to be very, very careful in a situation like that. Okay? Now, what do you suppose most affects your inertia? Let me ask you this. Which would have more inertia? A smart car or a semi-truck?
Semi-truck.
Why?
Because it's heavy.
It's heavy, right? Okay? Your inertia is measured by your mass. The more mass you have, the more likely you are to continue doing what you were already doing. Okay? Again, Newton's first law is not rocket science, it's common sense. Okay? If I've got a kid on a tricycle moving towards me at 20 kilometers an hour and a school bus moving towards me at 20 kilometers an hour and I can't get out of the way of both of them, I choose to be hit by the kid on the tricycle. Okay? Why? Because I can reach out and stop him. Okay? I can just reach out, grab the handlebars. He doesn't have enough inertia to hurt me. Okay? If I do that in front of the school bus, it's going to end very badly. Okay? I'm going to be a hood ornament, right, in that situation. It has more inertia because it has more mass. Okay? This is true in things like, you ever see a skinny sumo wrestler? Why not? Because they don't have enough inertia to win. Hey, think about it. Sumo wrestling is all about making somebody else move. Okay? It isn't even so much about strength. It's just about, if I'm really, really big, I'm hard to move. And especially if I get really low, I'm really hard to move. Okay? It's why you don't ever see a skinny sumo wrestler. They're easy to move. Okay? It's also why you don't see a skinny offensive lineman or defensive lineman. Maybe you do in some sports, or in some levels of football, but in professional football, they're all really big guys. Okay? You don't see a skinny lineman. You wouldn't want to be a quarterback with a skinny lineman. Okay, because you're going to get sacked all the time, right? You want someone big that's hard to move because they have lots of inertia. Making sense? Okay. So, inertia then, okay, is your tendency to continue doing what you were already doing. That could be nothing, okay? Like the desk, right? The desk's inertia right now is to sit there, and it'll continue to sit there, okay? Whereas a meteor coming towards the Earth is going to continue moving at a constant velocity until it's accelerated by the Earth, or it hits the Earth's atmosphere and starts to slow down. Okay? Either way. Okay, and any changes in velocity or inertia require a force. Okay? That's going to cause something to accelerate, okay? Either positively or negatively. Okay, now, force. You've got to understand what the word force means. Okay, a force is a push or a pull. Okay, so it's anything that's going to act on an object and possibly cause a change in velocity. Okay. Now, oh man, just had total brain fart. I forget where I was going with that. Don't you hate when that happens? I don't remember if I hate it when it happens. It happens all the time. It happens when you get old. Okay, so when we have any force acting. The force can be a push or it can be a pull. It's going to cause some change if it's unbalanced. That's where I was going with that now. That makes sense. Okay. Right now, for this desk, how many forces are acting on that desk? 2. How many of you are like, okay, I know one that's acting on it, what's the other one? I'm not sure. Okay, it's okay, because we haven't really talked about it yet. Okay? What's the force pulling down on the desk? Gravity. What keeps it from falling? Right. Okay? The floor keeps the desk from falling. Right now, the net force on the desk is 0. There are no unbalanced forces. That's why it continues to sit still. Okay? As soon as there's an unbalanced force, then the desk would move. Okay? But right now, gravity pulls the desk into the floor, and the floor pushes back with an equal amount of force in the opposite direction. Does that sound like a saying you've heard somewhere before? Every action has an equal and opposite reaction. That's in its third law. It's a couple weeks out yet, but that's another one the laws we'll go over. Okay? Right now, the net force acting on the desk is 0. If I lean on the desk, is the net force on the desk still 0? Is the desk moving? Then the net force is still 0. I might be pushing on the desk. I push on the desk pushes on the floor, and the floor just pushes back harder. Okay? The forces are still balanced. Okay? Net force is still 0. I'm not going to push that desk through the floor. Okay? Everybody all right with that? Okay. So, force is a vector quantity. It's got magnitude and direction. Okay? So just like velocity, just like displacement, just like acceleration. Right? So in this situation here with the tow truck, okay, the cable on the tow truck is pulling this direction at an angle. But which way is the car moving if the tow truck is towing the car? It's moving horizontally that way. Okay? So if the car is moving horizontally this way, okay, at a constant velocity, what other forces are acting on it? If it's moving at a constant velocity, are there any unbalanced forces? Let me restate Newton's first law for you. An object will continue to travel at a constant velocity unless acted upon by an external unbalanced force. The car is moving at a constant velocity. Are there any unbalanced forces? There aren't. Okay, so we know that the cable is pulling like this. What force, other forces are acting on the car? Gravity. Okay, so could I say then that this angled force has a horizontal component and a vertical component? Okay. Since the car is not moving vertically, what's the net force vertically? 0, right? If it isn't moving vertically, it's not accelerating vertically, there's no unbalanced forces vertically. So the cable's vertical component and the force of gravity are equal, but opposite. Right? Now, that cable also has a force forwards. But the car is moving at a constant velocity. What force is acting on it backwards? What force would be acting backwards on the car? Somebody's got to know. Drag, yeah, which we call friction in physics. Okay, that could be a combination of air resistance, rolling resistance, all of those things. They all combine to effectively be the force of friction. Okay? The forwards and the backwards cancel each other out. The ups and the downs cancel each other out. That car moves at a constant velocity. Okay, now, if this truck is just pulling away from a stoplight, then this force here might be unbalanced. It might be greater, would be greater than friction, and the car would accelerate horizontally. But it's still not moving vertically. Okay? Everybody all right with that? Now, when this car starts to move forwards, what's going to happen to the angle of the cable? Right? If the truck is stopped, the cable's probably hanging almost straight. Right? But if the truck starts to accelerate, the angle will change. The vertical components will stay balanced. The car's not moving vertically. Okay? But there's a greater force forwards. Okay? That greater force forwards, okay, causes that angle to change. Okay? All of these things are things that we observe, but we don't always understand why they're happening. That's what Newton's laws are going to tell us. Why do all these things that we observe in real life happen? Okay? You're going to look at the world in a totally different way after this unit. You'll see it like I see it. It's not scary. Okay? It just makes things make more sense. Okay, so once Homer got moving, he couldn't stop. Flailing doesn't do anything. There's not enough air in there for you to flap your arms. You're not a bird. Okay, it might produce some small amount of acceleration, but not enough to stop you. Okay, what changed his velocity was running into the experimental ant colony. Okay, he was moving. It wasn't. He hit it. It exerted a force on him that slowed him down. Okay, that's sort of making sense. So, if you run out of fuel and you're outside the spacecraft, you're going to what? Float into eternity, because you would have no way to change your velocity. This is a big deal for the people that come up with like courses and things like that for spacecraft. Okay? They have to know how much fuel is present, okay, so that they can make the changes to the course or the velocity of the spacecraft without exhausting its fuel supply. Once its fuel supply is exhausted, it can no longer make any course corrections. Okay? So when they sent New Horizons out to Pluto, okay, they got it going really fast. They did a couple of gravity assists where they flew around some of the other planets in the solar system to get it going faster, okay, because they didn't want to waste fuel on changing its magnitude of its velocity. Okay? They wanted to save the fuel for course corrections that would steer it in other directions. Now, New Horizons wasn't very big. It was the size of maybe like a small golf cart. Okay? It was like quite small. Okay? So it couldn't carry a lot of fuel on board. So when you're deciding, okay, I need to move my spacecraft from this course to this course, okay, you got to plan that way ahead of time. Because if you wait until the last minute, you're going to use way more fuel to make that course correction because you got to go a lot further. If you make it early, just a small change will cause that angle to form and you'll get to the right place. Okay, so these people have to think of these things way, way in advance and make those corrections, and then they don't have to exert as much force or as much force for as long, and thus they use less fuel. Okay. All right, so we're going to watch a video here and we're going to see kind of what's wrong with it in terms of Newton. Woody's noble sacrifice. Okay? So the lesson here is Newton's first law can be real trouble for you in a lot of situations if you're not prepared for it. Okay? Now, there was not much they could do there. They had to get to that resupply module. That was probably still the best way to do it. Okay? Now, if you're not moving very fast in space, are there some things you could do to stop yourself that wouldn't require you to use fuel? You would use Newton's third law. Every action has an equal and opposite reaction. Anything that I can get rid of, I can use to exert a force on me in the other direction. So let's say I have a big heavy wrench attached to my spacesuit. Okay? So if I push on that wrench, what does the wrench do to me? Pushes back. In the same way that if I go up to the wall, okay, if I push on the wall, I push the wall that way, what does the wall do? Pushes back. I didn't push off the wall, I pushed the wall. The wall pushed me the other way. Okay? So if I have a big heavy wrench or a toolbox or something like that, and I push it away from me, it'll make me go in the other direction, or at least accelerate in the other direction. Okay? That could be useful, right? It might change my velocity enough, okay, at least a little bit, right? But how many times do I get to do it? Once. I have to let go of it, okay? Because I've had people say, well, why wouldn't you just like not let go of the wrench? And I'm like, because this is what you'll look like in space. Will you go anywhere? You're pushing on the wrench. Now when you stop the wrench, you're pulling on the wrench. What does the wrench do? Pulls back, and you're just going to sit there looking like you're dancing in space, okay? And nothing's going to happen. You have to let go of the object, because if you stop it, you've just done the exact opposite of what you were doing before. Okay? All right. Is this making sense? Okay, so this is all Newton's first law stuff. Okay? And we did say that Newton's first law is very much dependent on mass. So, who wins in a crash between a smart car and a semi-truck? Every single time, a semi-truck. Right? Why? It has more mass. Exactly. Okay? In any crash, there's a winner and a loser. Okay? Make no mistake. There's a winner and a loser in every crash. The winner is the object whose velocity changes less. Okay? And how much your velocity changes is dependent on your mass. Because here's the weird thing. When a semi-truck and a smart car collide, even if it's head-on, the forces are equal. So when the smart car and the semi-truck run into each other, the force that the smart car exerts on the semi-truck is equal to the force that the semi-truck exerts back on the car. That's Newton's third law. Reaction is an equal opposite reaction. Never looks that way though, because what do we see? We see the semi-truck basically completely unaffected, and soon the smart car is moving in reverse. Okay? That has nothing to do with the forces. It has to do with the difference in mass. And the difference in mass is what affects your acceleration. It's acceleration that hurts you, not force. Okay? It's the acceleration that force can produce that hurts you. Okay? So the person in the semi-truck experiences very little acceleration. The person in the smart car experiences a great deal of acceleration. Okay? I was once in a crash where a lady turned left in front of us. Okay? We were driving a Ford Expedition, big SUV. Okay? Big, nice and heavy, because I like to drive big, heavy things because I understand physics. And I like to win if I'm in a crash. I'm very competitive. Okay? So she turns this little like Ford Focus in front of us. Okay? For whatever, how she didn't see us coming, I don't know. Okay? So we smashed into her. Okay? Continued moving forwards through the intersection. Okay? And her car was like crumpled up, airbags were deployed, okay? And she was pushed backwards through the intersection. I continued to move forwards. Didn't even deploy the airbags because they're dependent on my acceleration. My acceleration wasn't sufficient because I have more mass. Because I won. Okay? Being more massive means you win. Okay? So think about that when you're choosing a car. Okay? If you want to be safer, the most important safety device in your car isn't a device at all. It's how much car there is. Okay? The bigger your car, the safer you will be. You will use more fuel. Yes, because it takes more energy to move something that's big. And yeah, it's not going to be as fuel efficient, but it's safer. Mass is what matters in a crash. All your safety devices, they're great. Brakes, airbags, okay, all that stuff. Yeah, they're all important. Crumple zones on the car, they're all important. But nothing makes up for mass. It's why you never see a semi-truck lose a crash, unless it's with a tank. Okay? They're always going to win because they have more mass, and so their speed doesn't change as much. Yep. Okay. And to show you here, this is actually dash cam footage of a crash my cousin was involved in. She got her pelvis broken, femur broken, okay, in this because the guy was on his phone. Don't do that. Okay, so my cousin is in the car in front of this Nissan Altima here that you see. Hers is the little white car you can see through the window. Okay, now, they've got a green light, but there's a distracted driver coming in from the left. Okay, she's in quite a small car. He's in an SUV. Okay. Okay, so, I mean, she wasn't moving very fast, and it's perpendicular, okay? He only hit the brakes in about here, right? And then when he smashed into the car, and so, right there is where you see like the first evidence of braking, okay? And then into the car. Now you can see that changes the speed and direction of my cousin's car considerably, right? Because her car has less mass than the other vehicle. Okay? That sort of makes sense? Yeah? Now, this is in Hawaii. She actually lives in Hawaii. This is one of the rare places where in Hawaii you actually see concrete traffic barriers. Okay?
What's up with the green car? Did that get hit too?
Yeah. That car luckily got clipped. I think she probably would have been killed had that car not been clipped first. That's actually what caused him to hit the brakes, was seeing that car. He hit that car first, and it slowed him down probably just enough, because she was very badly injured. Like, I mean, we're talking like a crushed pelvis, right? Broken femur, pretty serious injuries. Had he not clipped that car first, I think it probably would have killed her. So yeah, what you see here is these concrete barriers, but you can actually see right here, back it up a little bit, see all these orange things here? You don't see them in Canada. We don't use them. What are they full of? Water. Okay? They're great traffic barriers, because if you hit them, because the water is a fluid, okay, you get a lot less damage. And it's a lot safer to hit that full of water.
Good
because you
afternoon,
can change
everyone.
shape.
Sorry for the interruption.
It doesn't work in Canada because most of the year they're frozen solid and they're concrete
This is a reminder to
anyway.
all grade 12 students during nighttime today, you will be completing your fall grad